Greetings, everybody. I hope you're comfortable and that you would rather be here than in the best hospital in Waco. And hopefully we'll learn some good stuff today. Before we start, any questions on anything to do with anything relevant or irrelevant? Yes. No? Okay. Let me go ahead and start with something that I should have put back with the fuzzy, because I think this is very interesting. So this is a fuzzy topic. I keep resurrecting fuzzy with the case, for example, of Combs control, which was not fuzzy. It's more of a design philosophy. Excuse me. So let me go ahead and start sharing the screen and just show you something very interesting, because I know that you all love this stuff. Let's see. Okay, I shared the wrong stuff. Okay, this is something with fuzzy resemblance. What I wanted to show you here today is kind of an algebra that comes out of fuzzy logic, which is really interesting. This is fuzzy composition and an introduction to resemblance. And on the left is, well, just let me ask you this. Okay, I'm trying to get my little special pin to work. Let me unplug it and plug it in, the old Microsoft reboot. Okay, my old Microsoft reboot does not work. Let me try something else. Okay, it might be this. Okay, that didn't work. I'm going to try one more thing. And if this doesn't work, I'll just have to cancel class. Okay, something is funny. And no, I was just joking about canceling class. Okay, let's see. It goes here, wraps around here, goes up to here, and dun, 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 dun. Yes, okay, good. Okay, I'm going to see your film history knowledge. Does anybody? Okay, it's not writing on my screen. Why isn't it writing on my screen? I don't know. Let's see. Okay, everybody sees this, and it's still not writing on my screen. And oh, because I haven't, have I shared it? No, I don't think I've shared it. No, I've shared it. Oh, there we go. Okay. Okay. Should have had this all checked out before we started, but I didn't. So here it is. Anybody know who this is? Okay, that's Stan Laurel. He was one of the great comedians, along with his partner Oliver Hardy, in the Laurel and Hardy comedies, and was one of the few that actually made the transition between the silent years and the talkies. If you go to YouTube and you put in Laurel and Hardy, you will come up with some hilarious videos. They're in black and white, but they're still hilarious. They really have survived the gift of time, the trials of time, whatever. Anybody who knows who this is? No? Okay. That's a guy named John Kerry. He ran for president, and he lost. And let's see, I think he ran against George W. Bush, and now he's going around the world in his private jet because he married the widow of the Heinz ketchup ketchup fortune, and he's independently rich and likes to go around the world in his private jet talking about climate change. So I put those here because they kind of resemble themselves. They resemble each other, at least in terms of their smiles. So with that, let me go over here and see if I can figure out how to heck to go to the next screen. I don't understand what is going on here. Okay, I'm trying the down arrow. That doesn't work. I'm trying the down arrow here. I'm trying the return. Let me see if I can go to the full screen. Let me go up and turn off the, you know what? I just did an, shoot. I just did an update of Zoom. And this is the thanks I get for doing an update of Zoom. So no more Zoom updates, or maybe another update, I guess. Okay. So here's a resemblance, and this is, we're going to use a fuzzy metric here. This is my, okay, this is my son Joshua in the upper left. Maybe I'll just use my cursor. Can you see my cursor? Give me a thumbs up if you can. Okay. This is my son Joshua. And people say that he's a doppelganger for Matt Damon. And the resemblance between Josh and this guy is, we're going to say a 0.8. Okay. And again, this is a fuzzy measure because resemblance is not ordinal. My resemblance to him, this is an old picture back where I used to put dye on my beard. That's a 0.1. And Joshua and who is that? Tom Cruise have a resemblance of 0.2, whereas between me and Tom Cruise is about a 0.9. Would you agree? Okay, that's supposed to be kind of a joke. Okay, so we have this, and what we can do is we can write a, an if-then rule. Matt Damon resembles Tom Cruise. Okay, so Matt Damon resembles Tom Cruise. Now here we just have the resemblance between two guys in this relationship. So we're taking indirect evidence to look at resemblance. So if Matt Damon resembles Tom Cruise, if Matt Damon resembles Josh and Josh resembles Tom Cruise, is that right? Or Matt Damon resembles the professor and the professor resembles Tom Cruise. So these are simple if-then statements that we can put on there. And with the knowledge that we have and also the Zada min max, we can figure this out. It's the maximum of the minimum of 0.8, 0.2. So it turns out to be a 0.2 if you go through the mins and the maxes. So Matt Damon does not resemble Tom Cruise. At least through this indirect method, we have a 0.2 relationship. Now notice what we do is we go down the first column and we get a 0.2. We go down the second column, we get a 0.1. Then we go across this and get a max in order to get this relationship. Well, let's do another one. Well, let's talk about this in terms of inner products. You're all familiar with inner products. On the bottom left, we have an inner product where you do the sum of the product. So it's this times this plus this times this plus this times this plus this times this, and that then is equal to your following result. So that's how you multiply two vectors and get a scalar. And what we're doing is we're doing a operation on this with the second column. And what we're literally doing is we are doing kind of a matrix vector or a vector multiply, except that instead of multiply, we do mins. Instead of adds, we do maxes. Instead of multiplies, we do mins. Instead of adds, we do maxes. So I'm going to try to draw on this. Let's see if this works. So therefore, the way we would do this is the minimum of 0.8 and 0.2. Okay. And then we would do the minimum of 0.1 and 0.9. And then we would take the maximum of those two. For the first case, the minimum of 0.8 and 0.2 is what? 0.2, right? The minimum of 0.1 and 0.9 is 0.1. So notice we've done exactly like the multiplication addition thing of doing an inner product shown on the bottom left, except that we have used min for multiplication and max for addition. And that allows us to get the correct result. And my controls are not working, so apparently I have to stop sharing and share again. So the composition operator 0 is the same as the conventional matrix operator. This is just what I said. So here's a longer example. We have this. Anybody know who this is on the upper left-hand corner? What movie this is from?
Planet of the Apes.
Planet of the Apes. That's right. It was a lady from Planet of the Apes. You can tell she's a woman because of the eye makeup and the lipstick. And we want to look at the resemblance between her and all of the people down here. And we are going to make just a guess. I would say 0.0, 0.1, 0.3, 0.5, and et cetera. And so we get this vector, if you will, of resemblance. And now I'm going to do Michael Jackson, the late Michael Jackson, and I'm going to do a resemblance between all of his. So this is 0.4, 0.6, 0.7, and 0. So my takeaway is that this guy, anybody know who this guy is? I am so glad you don't know who this is. I'm not going to tell you. Anybody know who this is? Wow, am I getting old? Okay. This is, I forget his first name, but his last name is Stern. He's a shock jock. This is Frank Zappa, used to be a musician.
Is it Howard Stern?
Howard Stern. Yeah, it's Howard Stern. That's right. Okay. Yeah, kind of a vile guy. This is, oh, you got to know this. Okay, Trevor shook his head. Who is it, Trevor?
Hitler.
That's Hitler. That's right. So now from these two vectors, we would like to find out the resemblance of the lady from Planet of the Apes to Michael Jackson. And to do so, we take the composition. We take this top vector. We perform a composition with the bottom vector, just like an inner product, mins instead of multiplications, additions instead of maximization. And this turns out to be the strongest link. So the composition of this top one with the bottom one turns out to be 0.7. So we do the mins at 2 points at a time, and the min for here is 0.7 and 0.8. We do the max across those, and the resemblance turns out to be 0.7. And the strongest link between the monkey lady and Michael Jackson is a 0.7. So we can even extend this. Here we have a resemblance matrix of, anybody know who this guy is? No. Okay. Pee Wee Herman. Okay, Pee Wee Herman, yeah. And then we're going to do a composition with another guy. Now notice the row here, Michael Jackson, Pee Wee Herman, and the monkey lady is the same as the column here. Because in order to make a composition of these two rows or these two matrices, we have to have the dimensions match. And so what we're going to end up is with a relationship between Zappa and this guy and Howard Stern and the dog. just like we would multiply these two matrices together using the min for the multiplication, the zero for the max. And it turns out to be the matrix which is shown at the bottom. And so let's see how this bears out. If we do that, we get that Howard Stern and Frank Zappa is at 0.6. They're probably the most closely related in resemblance. Frank Zappa and the dog is 0.4. If you multiply these two matrices together, this guy in 0.5 and a 0.1. So this guy, whoever he is, I don't know who that is, has a resemblance of this guy of 0.1. So the big takeaway here is you can do these matrix multiplications. You do come up with these in fuzzy logic, are just exactly like multiplication for mins, or mins for multiplication, and maxes for addition. It's exactly the same matrix algebra that you're used to and love. Okay, any questions? Okay, good. I meant to show you that back with the fuzzy logic lectures, but I simply forgot to. Okay, next I want to show you, let's see if I can find it here. I got 70 million windows open. Okay, I'm going to show you something called particle swarm. Particle swarm was one of these cases where there was just an explosion of interest. And then after the explosion of interest, it kind of has died out. It's still a viable way of doing search. And in fact, remember the problem that Adam Goad talked about with the simulated annealing? I want him to try the same thing with particle swarm, because I think that would be a good thing to do. Let me explain to you the history of this. It was founded by actually a friend of mine, Russ Eberhardt, and one of his colleagues named Kennedy. And Kennedy was a bird guy. What do they call bird guys? Are they ornithologists? I think they're called ornithologists.
It's a ornithologist.
Ornithologists. Thank you, Colin. Thank you. This was really interesting. I used to have a good friend that was an ornithologist at the University of Washington in Seattle when I worked there. And his wife said, don't go to the movies with him. Do you ever have somebody go to the movie and in the middle, they start pointing out little discrepancies, little things that you didn't notice that bug them? I have an ex-policeman that I sometimes watch movies with, and he would always point out, a policeman would never approach a house in that fashion, all bunched up. They would spread out in order to minimize their vulnerability. Okay. And he's there talking and the movie's going on. Well, this guy apparently did the same thing. And I said, what can an ornithologist do to ruin a movie? And she says, well, we went and saw Out of Africa, and you hear these animal sounds in the background, like, ee, ee, and those sort of things. And in the middle of the movie, he says, that's not an African bird, that's a South American warbler or something like that. So he was sitting there doing that all during the movie about the bird sounds. So everybody can ruin the movie with their own expertise. Anyway, this ornithologist had a certain model that he was using for bird migration. And have you ever seen a flock of birds fly and they're all kind of flying together? And then all of a sudden they seem to move, they seem to have a turn, and they do something else. He was trying to come up with a model to explain this. And the model he came up with, I don't know, to me isn't very realistic, but it was a model that he was applying, and he was looking at empirical results and trying to say that, there's some semblance between the way that birds fly and this model. And so he got together with Russ Eberhardt, and this really is great, by the way. If you get two people in orthogonal fields that get together, sometimes you just get great, incredible results. And that was the case with Russ Eberhardt and this ornithologist called Kennedy. And they came up with this thing called particle swarm optimization. And Eberhardt, who has written a couple of neural networks books, really, really good neural networks books, he says, I wonder how this works in training a neural network. because this particle swarm optimization, they should have called it flock optimization or something, but it was a particle swarm optimization. It was a way to perform optimization. We've seen training as a way to, or search is what we do when we train neural networks, right? We talked about error back propagation. Yeah, that was one way to train a neural network. So he set up a neural network, and he went out and he decided he would eat lunch. Now, the neural network, the computing speed at the time was such that that neural network should have taken like 6 or 8 hours to train. He came back after lunch and he was surprised that this neural network had trained, really, really quickly. And the reason that it trained really, really quickly is that the particle swarm optimization is a multi-agent sort of search. And as I'll point out, has some features which I don't see in other multi-agent optimization results. And anyway, this amazed him. So he and Kennedy wrote a paper. It was cited, 10 billion times. And it turns out historically what happened to particle swarm. I think it's still a viable way of doing search in a dimension which is manageable. If you think of a neural network, every weight is an axis in a higher dimension. So if you count all the weights in your neural network, you might have 1,000 weights. So you're doing a search in 1,000-dimensional space. Your landscape is 1,000-dimensional curve, and you're trying to find the maximum or minimum or whatever you want to do. And this was well and good, but today's work in deep learning is such that they have millions, maybe billions of different parameters that they have to optimize. And in order for the particle swarm to work, you have to observe the whole space. In other words, if you were to apply a particle swarm to a training of a neural network deep learning, you would have to put in one input, figure out what the result is, and you would have to put in another input, and you would have to figure out what the result was. Then you'd have to go back and you'd have to combine those inputs and redo it again. It was just too big of a dimensional thing to handle. So that's the reason today we use error back propagation, because if you recall, error back propagation had this beautiful property that two neurons were connected by a weight, and the update of the weight in error back propagation was only a function of the numbers associated with the two neurons. So it was all a local phenomenon. In the case of particle swarm, or just about any other neural network training algorithm that I can think of, it's a global thing. You have to look at all the weights at once in order to perform the optimization. And that just got too unwieldy for these larger problems. However, Eberhardt was able to show that in the neural networks that he used, which were layered perceptrons, that particle swarm was incredibly effective. We saw it adapted and used for many, many different things. So I'm going to give you an explanation of particle swarm optimization, and I'm going to tell you something remarkable. The particle optimization can be performed with, are you ready? 2 lines of code. So not only is it powerful, it's amazingly easy to code up. So let's do that. And I will try to, with some degree of semblance, share my screen. Okay, can you see there should be 4 panels on your screen. Do you see those? Okay, good. Thank you. Thank you, guys. Okay, so I will make these a little bit bigger, and the version I have of this, which I'll make available on the spreadsheet, gives a background of particle swarm optimization. And this is a multi-agent optimization, just like evolutionary search. But unlike evolutionary search, this works a lot better in general. So let's talk about it. We have single search techniques. This is particle swarm optimization versus single search techniques. And if you recall that something like error back propagation just has one agent, which is looking for the maximum. And there's ways that you can get around this, for example, by using the simulated annealing. But typically you go to the extrema. The extrema is either the maximum or minimum, dependent on where you start your search at. So here, if you started the search here, you get here. If you started a search here, you went to the purple dot here. If you started on the red dot, you went to the red dot, et cetera, et cetera. Particle swarm optimization is not a single agent search. For the single agent search, you would either get the purple dot, the blue dot, or the red dot, depending on your initializations. Particle swarm optimization, however, puts a lot of different particles out here. For some reason, Eberhardt and Kennedy did not talk about these as birds, but as particles, because they're little dots, I guess, was the reason. But this was invented by James Kennedy and Russell Eberhardt. The algorithm originally developed to imitate the motion of a flock of birds. I'm reading on the right-hand screen. It assumes an information exchange. Do you remember in multi-agent search that you had a bunch of people exploring the fitness landscape and they were talking to each other on walkie-talkies? And the basic idea is to keep track of the global best and the self-best. For example, if a bird is flying over the landscape, the only thing the bird can do is it can look down. But that bird can also have memory. It can say, you know, I'm going to look down, but okay, this is not, I saw a better result back there. And then it goes to another place and said, no, this isn't as good. I saw a better result back there. And then it goes to another one and says, you know what, that's better than I've ever seen before. And so all of a sudden its local best, which is the best solution that it ever had in its history, is replaced by this new result, which you know is a better result. And so that is the self-best. Then there's the global best. The global best is the aggregation of all of the self-bests. You look at all of the self-bests and you take the maximum of that, or you take the one that's, well, let's say we're trying to maximize. You take the maximum of that and you try to generate, well, you take the maximum and you try to generate the global best, which is a single number, which is shared by all of the birds. So all of the birds know the local best and the self-best. So how does it work? And by the way, this is interesting. You remember we talked about the flock of birds going up here, and then they were kind of flying, and then they all of a sudden they changed direction. According to the Kennedy model, at this point, this pivot point where they changed direction was a change in global best. So all of the birds knew that the global best was changing, and so they pursued a different direction. The degree to which that's true, the degree to which that's accepted today, I don't know. But this was Kennedy's model. It doesn't seem to me to be applicable because I don't think the birds are foraging. I don't know. I'm not an ornithologist. So how does it work? We want to find an X. We want to find some value of X, which maximizes an F of X. So X is the dimension of your search space. For a neural network, this would be a vector of all of the possible weights that existed. And this function of X would be an overlying fitness function. And so here's how it starts. It's pretty simple. It starts with a random set of solution vectors. So in other words, you populate the space with just random vectors. And you do include randomness in the choice of the, well, you update those dates, but update those positions, but randomness is used in the update. And you encode the information about good solutions, as I mentioned, the self-best and the global best, and then you use the experience information to imitate search of new regions. So here we have it. We have a bird, and this bird is flying in one direction. Now, what is the next step that is going to be? This bird has a history of back here. It knows where it flew over the best solution that it's seen so far. So what it does, it takes a vector of the distance to the to the personal best, and then it takes a vector in the direction of the global best, and then it combines those into the new motion. So it combines both the information of its previous best and of its current best. And that's the way that it determines which way to fly. So the only thing that the bird needs to figure out is not what the global best was, but it needs to figure out what the coordinates of, not the global best. Well, both for the global best and the personal best, come to think of it. It doesn't need to know what the global best or the personal best was. It only needs to know the coordinates of it. Now, eventually it's going to have to find out the value of the fitness at that point. But that's the only thing that it has to remember in order to do the update. So each particle, each bird remembers where the global best was and where the local best is. And here is the update. X is the position of the new bird, and this is the step. So this is the position of the bird over this very high in this high dimensional space. And so wherever that bird is at, it takes the old position over the landscape and it adds a term. In other words, that term tells it where to step next. That's going to be an incremental term. And like we said, all search algorithms require parameters. And so here is the way that this V vector is computed. That's the next step of the bird over the landscape. It's determined by some weights here, some W times the previous vector. Now, why do they use the previous vector? The previous vector, if we make the new step have a component which is the old step, that mixes in momentum. In other words, the bird cannot go whoop, whoop. It can't change direction. Its new step must be in the general direction of the old step. And here's where the self best comes in. You take in the self best and you subtract where the bird is at. Now, what is that? If you subtract two vectors, you get a vector that connects the two vectors, right? If you subtract two vectors, you get a vector which connects the two vectors. So this difference is the vector that is pointing towards the self best. And likewise down here, you take a vector which is the group best minus the current location. That is the distance to the that is the distance to the group set. Okay. And then you multiply them by random numbers. This is kind of interesting, but you multiply them by random numbers. We said that random numbers had a big effect in search. So yeah, we add some here. And so in a way, the relationship and the degree that these two are interrelating is determined by randomness. And these random numbers are usually chosen to be uniform on the interval from 0 to A1. Why is this? Because it worked. It worked in the Kennedy-Eberhardt thing, and it worked in a lot of other results. There are, anytime that you have a really hot paper published, there are 1,000, I'll call them 3dB papers. You know what 3dB is? 3dB is the minimum amount of volume that you can increase a sound and a person can notice a difference. And so these 3dB papers were simply little increments to the overall publication of the particle swarm algorithm. But notice this is 2 lines of code, simply 2 lines of code. And you have to remember the self best and you have to remember the group best. And once you do that, these 2 lines of code tell you where to go. So this is a little bit of breakdown of just what I explained, V of K. And this is called, I don't like this term, but it's called the collective consciousness, because the birds are sharing this global best. So I've heard this called the collective consciousness, where this has nothing to do with consciousness at all, at least any of the definitions I'm aware. And this is self-consciousness. This is just consciousness of what you're doing when you talk about the self best. So the relationship of the variables is x is a solution vector, and that is referred to as a particle. V is the velocity of the particle, but really it isn't the velocity of the particle, it's the step size. That's really probably inappropriate. I guess you could do a step size into a velocity, but it's actually the step size. A1 and A2 are scalars. Now, what are the scalars? If you go over to the left, the random numbers are distributed uniformly between 0 and A1 and 0 and A2. Kennedy and Eberhardt make some suggestions, and there's been lots of other publications which come up with different ways and different distributions, and they claim they're better. We know from the no-leaf free lunch theorem that these were better only because they work better on the problem that they were considering. W here, which is the coefficient of the old vector, is the inertia, and that keeps the bird from turning, way down. And R sub 0, 1 is a uniform number between 0 and 1. And so you can think of just A1 times this R of 0, 1 as being the weight of the vector. You notice that the way that the random variable is chosen, that random number is always positive. So you never have a reversal. You never have that R term become negative. Okay, now I want to pause and I want to try to, I want to stop sharing. And I want to explain the idea of neural network inversion, its relationship to GANs, and then its relationship to particle swarm. So, can everybody see my white screen? Okay, good, thank you. So we have a neural network, and this neural network, if it's done as a classifier, we have an input, we have a bunch of weights here, and I won't try to draw in all the weights, and we have a corresponding output. The first person to do neural network inversion that I'm aware of was also Russ Eberhardt, the guy that did the particle swarm. And here's what Russ Eberhardt did. He looked at diseases and diagnosis of diseases. And over here were symptoms. And over here was some relationship of the disease. So Eberhardt, who was at the time at Johns Hopkins University, I think it's their applied physics lab, had access to all of this data that he was able to train the neural network with. And, what's the ultimate aim here? The ultimate aim is to take a neural network and get rid of the doctor. Somebody comes in with symptoms, they give the symptoms, and then the neural network does the disease. You think there's something which would catch on, and it actually did pretty well. And in fact, the neural networks of today do very well. But you're never gonna take the doctor out of the loop. First of all, they're too powerful of a political force, and second of all, you need the doctor in there for nuances, for little variations. So here was the case. You trained this neural network. Now, what did you do in this neural network? In this neural network, this was fixed. And this was fixed, right? In other words, the training data, for all intents and purposes, is fixed. And then what do you do with the weights? You wiggle the weights, right? This is your search space. And by wiggling the weights, you train the neural network, even for deep things and deep convolutional neural networks, whatever. Okay, imagine the same thing, and except now we're going to ask the neural network something different. We're going to say, I want a disease, say scurvy. Okay. say one of the solutions is scurvy. Did I spell it right? Anybody know how to spell scurvy? That's good. Okay. And here's what you want to do. You want to find out the input, the symptoms that generate scurvy. This is kind of like a Bayes rule, if you will. Okay. We've trained it in the forward fashion on the data. Now it's trained. We want to do a new, scurvy. What symptoms would give you scurvy? And so what we would do is we would now fix the output. We would fix the weights because the neural network is fixed. And we would wiggle the input. So our search up here, our search at the top is for the best value of weights. Our search at the bottom is the best search for inputs that give you scurvy as the output. Does this make sense? This is referred to as neural network inversion. You're inverting the neural network. And this can be valuable very nicely. Now, this is related to the GAN in the following sense. And by the way, this was used quite a bit. There's so many scenarios where you have the forward problem solved and you want to do the inverse problem. In physics, there are things called inverse problems. You've probably heard of them. You can, for example, take an image, run it through some optics and get an output. The inverse problem is given an output and given the system, the media went through, what's the corresponding input. So inverse operations are ubiquitous all over the place. And this was a way to address the inverse problem is through neural network inversion. Now, there was a problem with this. Oh, well, before I go to that, let me give you a kind of an interesting result. Sometimes you go to a source, an oracle, and what happens with the oracle, you pay the oracle money and it gives you the right result. The oracle is a source of training data. The oracle is a source of training data. So you get a bunch of training data and it fills up your search space. So you have a bunch of X's. We're just going to do a binary classification here for the purposes, for the ease. And so we get a bunch of things and we get a bunch of things outside the class. Maybe we're trying to recognize skunks versus things that aren't skunks, okay? Now, as we have talked about previously, there is a true boundary between skunks and not skunks. There is a boundary between skunks and not skunks, but the best we can do in a neural network is kind of approximate that, right? And the more training data we have and the better we train, the better this brown curve meets or the dash curve meets the solid curve, right? The more we train. Now, we have an oracle up here. Now, this oracle, if we give it a coordinate, it will tell us whether it's a skunk or not a skunk, okay? This oracle will tell us if it's a skunk or not a skunk. But every time you ask it something, you have to pay in order to get the result. There's numerous results of that. One is that if your data is generated by a simulation, you have to pay for the computation time. Some of the work that's done for the Navy, for example, maybe you need some data which is only available if you go out on a ship and do some sonar measurements, for example. So you have to pay for another trip for the ship. But anyway, the entire idea is that in some fashion, you have to pay the oracle for the result. So the idea is you want to spend as little as you possibly can on the oracle. So the question is you can get any of these results. You can get any point here, take it to the oracle. Okay. And that oracle will say it's skunk or not skunk. So the question now, which is kind of obvious, is where should you choose these points to take to the oracle?
I feel like it has something to do with interval halving.
No. Okay. Nice try. No cigar. Let me take another example. Suppose that we were to do in the middle trees and on the outside was bushes. So we're trying to do a difference between trees and bushes. Where would be the most ambiguity between trees and bushes? It would be something like a bonsai tree or something like that, right? In other words, there would be confusion. And where does that bonsai tree live in this graph that I have written down here? It lives right on the boundary. Because you shove it a little one way, it's a bush. If you shove it if you shove it the other way, it's going to be a tree, right? So the point, well, let me make another thing. If I ask for a point up here, would that help me at all? No, it's so far from the boundary. It's very clear what this classification is, right? It's so far from the boundary. It's very clear that this is a 0. We don't have to do anything. If I ask something in here, yeah, it's very clear that it's going to be an X since it's far from the boundary, right? So it's clearly a tree or a bush in that case. Where the maximum ambiguity lives is right on the boundary.
Dr. Marks, if you don't know where the boundary is, couldn't you use interval halving on 2 opposing results?
But here's the thing, you do know where the boundary is because what I'm
Oh.
going to say, okay, maybe I didn't make this clear. You have a partially trained neural network.
Ah,
Okay. And I should just do one output. And yeah, sorry about that. So an output of 1 is going to be a 0. An output of -1 is going to be an X. Okay. So if you have an output of a 0.6, what would you say? You would say, yeah, that's a 0 because that's closest to 1. If you had an output of -0.6, what would you say? You would say that that'd probably be a 1. What is the point of maximum ambiguity? Your output for this scenario would be what? 0. If your output is 0, then you are right on the edge of the classifier. If the output is 0, you're right on the edge of the classifier. So that's what we would like. We would like to invert the neural network for values that give us only a 0. Does that make sense? And if we have an output of a 0 and we get the corresponding input, that input is going to lie on this boundary, isn't it? So therefore, in order to maximize your money and not to pay this oracle big bucks, you would like to get the best possible training data from additional oracles. So you'd like your biggest bang for the buck, and this biggest bang for the buck comes from resolving these points of maximum ambiguity. Okay. And so this is an example of this idea of inversion. You take this 0, the 0 is fixed. You have these weights which are fixed. And then you have this input, which is what you wiggle. So what would be your error here? Your error would be what you got minus 0, and then you want 0. So anything deviating from 0 would be the error. Now, it isn't clear, but there is an algorithm where you can use error backpropagation, a variation of error backpropagation to perform this operation, but it doesn't need to be error backpropagation. In fact, it could be particle swarm. It could be any sort of inversion that you wanted in order to get the inversion. And so this is the idea of querying the neural network in order to get better results. Now, this relates to the GAN, which Glauco talked about. And I'm going to explain this in very rough scenario, this is pretty close. Again, you have a search space, and then say that you're trying to generate deep fakes of faces. What happens is you have a bunch of deep of actual photos here. And this populates the space, but it doesn't populate the space well enough. It doesn't populate it well enough. So along comes the GAN, and what the GAN basically allows you to do in the most rough sense is kind of fill in this portion of the space with other things that resemble faces. So you can you see that in a way, this is kind of an inversion of the neural networks, because we're finding internal points to the training data, other representative points. And so the GAN, in a way, is repopulating this, and in a way, it's kind of defining this. Now, with GANs in general, you just look at the good guys. You don't look out here. And this is I'm sure that there's literature where you do look out there, but I think in general, you don't look out here. You just try to repopulate this space and to determine whether you're in the space or not in the space. Let's return to the boundary condition where we're doing this inversion using a neural network. You know, one of the problems with inversion of the neural network is that it always goes to the same point. If you initialize the inversion, it goes here. If you initialize the inversion, it goes here. And the reason for that, is if you look at this boundary, I'm going to kind of draw the boundary. And then you look at the gradient of the boundaries. The gradients of the boundaries will look something like this. So what does that tell you? It tells you there's a sharp gradient here, that right here is a very steep, say we're minimizing, it's a very steep descent to zero, right? In other words, the hill here is very steep. So that if you put a ball here and you try to do maybe steepest descent, for example, that ball will always roll to the place where the hill is steepest. Does that make sense? So roughly that's what happens in this regular inversion of the boundary. You notice that the GAN doesn't do this. The GAN doesn't do this. But the reason I went through all of this is to, first of all, introduce you to the idea of neural network inversion, the use of an oracle. If you do have a training scenario where you have an oracle available and you have to pay for data in some sort of sense, the inversion is probably a very good idea. So with that, now let's return to the particle swarm. Where did my particle swarm go? You're kidding. It isn't here. Okay. I don't care. Oh, there it is. How did it get there? Okay. I don't know what's going on. Let's see. Bills. Okay, it's on my screen, but I don't see it as a possibility for a window to be open. So I'm going to share my screen and just kind of put it over top the screen. Okay, can everybody see what's going on here? These are the particle swarm slides. So here's kind of a question, and this relates to inversion. And the inversion is such that, do you see this picture here? The boundary that we want is the black kind of oval here. So it's a lot like neural network inversion where there's more than one inverse. And we would like to get, in order to get the best representation, we would like to get all of the representation within this black boundary here, and would like to do that using particle swarm. So this is kind of border edge detection. And here we have the birds flying around, and we would like each one of them to figure out a kind of a different point. Well, if you just do finding the points anywhere in the boundary, we have that convergence again. On the right is the actual curve that we have, but you see that, but you see these X's down here. See these itty bitty X's, right? That's where the convergence was too. And this was because of the gradient of the error sort of thing. These were where the birds ended up. It's not bad, but what we would like, it turns out that this fitness function we chose was a circle, and we would like it all the way around the circle. So what would you do? Recall my friend Mike Healy, who worked for Boeing and was referred to as a penalty function artist. You have to look at this problem, and you have to craft, you have to synthesize a fitness function that allows you to get to the result that you want. So therefore, instead of the metric of using the boundary value, the fitness function was changed from the boundary value to the distance to the closest neighbor, minus the distance to the closest neighbor. So what you were trying to do is you were trying to minimize the distance to the boundary, but you were trying to maximize your distance to the closest neighbor. So you're having these conflicting results, and you can see by simply changing this algorithm to include a fitness function this way, that we obtain the results which are shown over here. You see these X's down here? Do they show up on your screen? You can see that the X's are pretty well evenly shaped down here, simply because we were able to change the metric. And you'll notice particle swarm doesn't need any gradients. There's no gradients associated with this. You don't have to know which way's uphill or downhill. You just have to fly around and measure where you're at and your fitness for that. Then there's some other techniques that didn't work so well, but that's basically the idea of the particle swarm. Now, why does particle swarm work so well as opposed to something like evolutionary search? One of the reasons that particle swarms works well is that the birds keep flying. So here you have the personal minimum, or the personal best. It flies over the personal best. It doesn't get stuck there. You'll notice that a gradient search would probably go up and find the personal best. That would be at the top, maybe the top of a hill, and it would just stay there. It wouldn't move at all. Any gradient technique, such as backpropagation, would similarly suffer from that unless you impose something like simulated annealing. So these birds keep on flying. Even though that they've explored a certain region in the space, they keep on flying, and they keep on flying until the global best doesn't change very much. And when the global best doesn't change very much, they say, well, we've probably flown enough, and this global best is probably the optimal. But the secret of that, as opposed to, for example, evolutionary search, which is very, very similar, right? Evolutionary search, if you remember, was survival of the fittest, repopulation, and then mutation, is that even there you get an attraction to a specific location in your search space. And because you get that attraction to that certain space, you don't move. It's not conducive to the moving as much as particle swarm. So that, in my opinion, is why particle swarm works very well. But again, it only works well for moderate sorts of problems. If you go with very large neural networks, it isn't going to work. For smaller, moderate neural networks, it works very well. For some of your optimization, it works, some of the optimization problems that we have, it works very well. It's just a general idea. It's just another one of these search algorithms. But again, the compelling thing about it is that you never get stuck at a specific place. You keep on moving. Okay.
Dr. Marks, I have a
Yes.
quick question.
Sure.
Would you mind pulling up those slides on the particle swarm search? I just have a quick question about how that related to the boundary finding.
Oh, okay. Thank you. Yes, I understand. Okay.
So the graph, yeah. So the fitness landscape there on the right, would that be like a distance from zero in? So if you were to train a neural network, partially train it on the classifier, and so it has a pretty good idea of what the boundary is. There are still some regions where it has low confidence,
Yes.
where it has a result of zero. So is that fitness landscape like distance from zero of your predicted classification? And then
Yes.
you're trying to identify the whole boundary?
Each one of these is trying to find the minimum of this landscape. However, the minimum does not exist at a single point. It exists in the circle.
Okay.
And you would like to get a representation of this minimum at hopefully equidistance points.
Right.
And so in order to do that, you not only have to constrain yourself to minimize the distance, but you need to also, we used to joke about this and we give the birds bad breath, because the birds don't want to get close to each other because each one of them has bad breath. And so what they do is kind of space themselves out along this result. So the importance here too is that one size does not fit all in terms of search algorithms, and that the more insight that you can have about the problem that you are solving, the greater the domain expertise that you can incorporate into the search problem, and the better you will do. Like if we didn't have these graphics here, unfortunately, these are just two-dimensional graphics. What are you going to do with 20-dimensional graphics? There are still ways that you can mitigate that and kind of visualize that, but you do have to get down and appreciate what the results are. And plus, this two-dimensional, one of the things I've found out, if you run into problems in 2 dimensions, they're going to manifest themselves in higher dimensions. It can turn out that some of the higher dimensional problems do not manifest themselves in lower dimensions, but certainly the converse is true. Okay. Did that answer your question, Sam?
Yes.
Okay, good. Any additional questions then?
I have a kind of a quick question related to that. So if your network is, maybe it has a lot of dimensions, but it's really shallow. So like you can picture like a single layer neural network implemented maybe as an actual neural network or as a support vector machine with the correct kernel.
Yeah.
Could you just simply calculate the support vectors and interpolate between those using like a quadratic programming solver?
No, I believe that with the support, let's go with the layer perceptron, but with the support vector machine, in order to train it, you choose a kernel, and you go with it. You don't. So we're not talking about anything dynamic in the training. We're using static training, but we're also realizing that we're hoping that the neural network has something called plasticity. The plasticity means that a partially trained neural network can be trained additionally. And that would be, for example, the paying for the queries. Now, the plasticity of neural networks always isn't true. In fact, do you remember the squashing functions like this, right? Let's see, I'm trying to do them backwards. Okay, you have the squashing functions like the sigmoid, or there's a bunch of other squashing functions. Sometimes a neural network will get trained to the point where you are saturated in one of these limits of the sigmoid. So you're way out here. So any variations in the weights are not going to vary the state of the neural network. It's still wiggling around out here. It's saturated. So there are techniques to break neurons out of this, which is basically to bring that saturation right up to the knee of the neural network and give it a little bit more plasticity. I guess it would be the equivalent of electroshock therapy. You know, you boom, and all of the states of the neurons would do their thing. So yeah, I guess in general the idea is that the training that we're doing on the neural network or a vector support machine would be static. You have to choose the architecture of your neural network or choose the kernel for your vector support machine and then go from there. By the way, how do you know which neural network is best? Say you have some data and you trained, I don't know, 4 or 5 neural networks using different architectures, maybe different number of layers, different number of neurons in each layer. How would you determine which one is best?
Most
Oh, go ahead. I was going to say you could give it some test data, ideally near the classification, if it's classifier, near the classification border.
Let's say it's a classifier just for giggles.
Yeah, so you could give it some test data that it wasn't trained on, give all of them test data that wasn't trained on near the boundary. Whoever did best on that, I guess.
Yeah, so what you could do is actually look at the test data and see which one dips the lowest, right? I mean, that would be an obvious thing, but there's a problem of doing this. And I saw this a lot with financial data, people trying to forecast the market. They would come up with a neural network and they would train it using data. Then they would train it, then they would change the architecture, train it with the same data again. And then they would change the architecture. And finally, they got it to the point where that test data really, really dipped low. Does anybody see any problems with doing that?
Your model could be overfitting.
Well, what happens is you have inserted yourself in the learning. Because there's a man in the loop, you have inserted yourself into that iterative training, and you could have, as you said, Colin, get to the point where you're accidentally overfitting, and because there's a man in the loop, you become a part of the training process itself. So that's something that you want to avoid, and I saw that a lot in training of financial markets, where people would come up. And I was the co-chair of something called the IEEE Computational Intelligence Applied to Financial Engineering. And you had all these people coming up and they says, oh, I figured out a way to beat the market. And they would show us the neural network. Oh gosh, what was his name? Jack something. Anyway, he was the head of the United States Financial Engineering's organization. He says he never had to look at the data. Did I tell you this story? The only thing he had to look at is one thing. He asked them a single question. He said, this is really great. This is that you've beat the market. Now, what kind of car do you drive? So the bottom line was, if this was successful, these people would be rich, but they weren't. They were usually graduate students who, once they took that problem, if they were a man in the loop that had actually placed themselves as part of the training process, and they went out and they put it online and attempted to test it, it would simply not work. It would all fall apart. So that's one of the dangers in repetitive training of artificial neural networks. And one must be very, very careful to not put yourself as an element in the loop in the training. Okay. I don't know, did that answer your question, Colin? Okay, good. Any other comments at all?
I had a quick question about, you mentioned if you insert yourself into the training process, you can potentially have some negative effects. So I understand that if you're trying to train a general neural network and somebody enters the training process to fit the neural network to this specific problem, they could be reducing the effectiveness on a general scale because they're fitting it towards a specific problem. If you're trying to just solve a specific problem and you happen to notice something like that, is there a downside to entering the training process and helping it train? trying to
yeah,
see if there's another downside.
yeah. Well, first of all, there's a question to try a neural network tune, try a neural network tune, try a neural network tune. Then you're inserting yourself in the training process. You have less a danger of doing that if you say, here's a neural network I'm going to try, 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 and then train each one of those neural networks, because you're not part of the iterative sort of process.
Right.
So,
So is
yeah, the bottom line is how does it reduce to practice? And you got to dink around with your data and be honest with your data and make sure that when you're testing it, you really are objectively testing it in a disinterested sort of fashion.
okay. Yeah, that makes sense.
Yeah. And sometimes you might have not have enough data to do that. That's, but that's the beauty of kind of the modern age of neural networks, is now we have so much data that the richness of training sets is just enormous, and we don't have to be concerned with that. Any additional questions at all? Okay, thank you very much. Be of good cheer. We'll see you in a couple of days.